Okay, good morning. All right, so I have some IT issues here because this new document camera is not very happy with the station here, so there's no signal going into this Kaltura recording, and so it took me a while to figure that out. Hopefully we can resolve this issue next time, but for today's recording, you will only have the recording of the screen. And then maybe we can use the camera to also look at the screen up there as well. So that's the best we can do today. I will send a message to the IT department to fix that. Okay. All right, so welcome back. What I want to do today is to go through the two other sections of this chapter, chapter 1. Now, if you recall, on Wednesday, we talked about very basic principles on series, and then we talk about approximation, right? So it's a good review of these two topics. The same thing is going to happen today. We're going to talk about integration, something that you should have learned before. And I'm going to point out a couple ideas in this integration that can help you solve some problems of this course. Then we will move on to chapter 1.5 on counting, combinatorics. In between, I will highlight one or two main concepts of 1.4, which is the linear algebra, but we don't need that until probably the very last week of this course. So I can go back and discuss that later. So that's the plan for today. Now, a gentle reminder is that we have homework 0 due this evening. So please take your time to just do that exercise. It's very easy, basically just to make sure that you know how to use our computer system, you know where to submit the homework, and then draw me a turtle. Why turtle, right? Have you ever wondered why do I ask you to draw a turtle? I've been doing this experiment for a while, and there appears to be a very good correlation between your grade and the turtle that you draw. Apparently, I can look at the turtle. I can tell which student is very organized. I can look at the turtle. I can tell which student just wants to piss me off. I can easily tell. Okay. I can look at the turtle. I can tell very likely is it drawn by a guy or is it drawn by a girl. I can tell. So that's why this turtle is actually very meaningful. It tells me a lot. Before I know your face, before I know your work, before you have even taken the test, I sort of know who you are by just looking at the turtle, okay? And some students, they learn the turtle of drawing turtle frontal. Some students, they learn to draw turtle the side. Some students, they want to draw turtles upside down. That tells me the creativity level that you have. It actually tells you a lot. So if you have got the chance to teach, try this experiment. It's pretty fun. Okay, so I look forward to see your turtle image and to know more about you. Okay, so all right, so let's talk about the lecture material. Lecture 1.3 on integration. All right, so why do we want to talk about integration? Well, that's because there are a lot of problems in probability and distributions. They're continuous time domain. And that's why you want to calculate some of the areas under the curve, and that is naturally about integration. When you were in high school or when you were in freshman calculus, the two techniques that you have learned about doing integration is substitution or integration by parts. If you think about this more carefully, right? Your teacher will tell you, well, substitute e to the power x by y or something, right? Or integration by part, if it is a very difficult integral, then integration by part. I'm going to tell you two more tricks, okay? The first trick is this odd and even function. Okay, odd and even function. That will help you solve quite a bit of problems very quickly. There's another trick is integrating a probability density function will give you 1. Okay, what do I mean? Now, we don't have this discussion today, but then I can tell you in a couple words. If you try to integrate a normal distribution from minus infinity to infinity, it got to be 1 because you are checking out all the possible states. Okay, and then that will give you the entire sample space, and therefore the probability has to be 1. So if you ever wonder, okay, what is the probability of this function? Make sure that you recognize that this function that you're integrating is a probability density function, and there are only a few of those that you will learn in this course. And once you learn that, and you see the pattern, so make it 1. Okay, so that can save a lot of your time. But let me talk about this odd and even function for now. What is an even function and what is an odd function? An even function is defined as the following. You have this fx. If this is equal to f of minus x, you just call it an even function. Okay? And now, if you get fx equals to minus f minus x, this is called an odd function. Okay? So that's the definition. There's a very beautiful property of this even function and also the odd function. For even function, you just need to integrate. Okay? If you integrate from minus a to a, you can just integrate half of those, and you can double it. I can draw you a picture later on. Now, if you're integrating an odd function from minus a to a, you'll get 0. And here is the explanation. Oh, I should make this move. Okay? So here is the explanation. This is called an even function. Okay? An even function, you have the symmetry going on in this picture. And so if I want to integrate a function from minus a to a, now that got to be the same, minus a and a, right? Then you just need to integrate this function from 0 to a and just double that. So that would make your life a little bit easier. Not too much, but a little bit easier. If you have an odd function, you're integrating from minus a to a, well, that's very easy. It will be just 0. Okay? That can save you a ton of work. So you ask, how can this be useful? Let me give you this example. Okay, you're integrating this function, x squared minus 0.4 times x to the power 4 from minus 1 to 1 in dx. How do you do that? Well, it's just 2 times from 0 to 1 of x squared minus 0.4 of x to the power 4 dx. How do I know? Well, this is an even function. Okay, it is an even function because this guy, you call it fx, that has to be equal to f minus x. And put a negative number into this square and also the power 4, it will return you the same thing. So that's an even function. So I know I just need to calculate this. Now the rest is just simple calculus. So you have this 1 over 3 of x cubed minus 0.4 divided by 4, x 5 to the power 5. And then you integrate from 0 to 1. Okay? And plug the number in, you get 2 times 1 over 3 minus 0.4 divided by 5. Okay? And then you do the calculation. Right? So I don't think I need to go through that step. Right? But you see the point, right? So you, instead of calculating from minus 1 to 1, in that case, you need to substitute another 1 here, another 1 here. You have more to subtract and add. Please. Oh, that's because I can show this identity here. Okay, so let me do it once again. So the question is, how do I know this is even? So let's say fx equals to x squared minus 0.4 of x to the power 4, right? By definition of even, I need to look at f of minus x. Now, what is f minus x? It will be minus x squared minus 0.4 minus x to the power 4. And that's going to be the same as x squared minus 0.4 of x to the power 4. Right? So this fx is the same as this f minus x. And therefore, it is an even function. Okay? If you have a computer, you can actually plot the function, and you can see it is symmetric about the y-axis. So that is an even function. Is it OK? All right. Now, let's also work on an odd function example. So here is an example where you have this x times x squared divided by 2. OK, so the first thing you want to check, of course, you can plug in the formula, right? So you can plug in, all right, fx equals to x times e minus x squared divided by 2. And then I can look at f minus x. That's going to give me x minus x e minus or minus x squared divided by 2. But that's just the same as this x squared, right? So you have minus x e to the power minus x squared divided by 2. So that means your fx is going to be the same as minus of f minus x. And so this is an odd function. So that's a proof. But you can also just draw the figure. This part is the exponentially decaying function on two tails. You will learn this function very soon. It's going to be like this. Okay? So that is the e to the power minus x squared. And then I have this x sitting in front. Well, that's going to change the function to this. This is the x times e minus x squared divided by 2. Now, this is e to the power x squared divided by 2. Right? Now, you see this function, and then you look at this. This is asymmetric about the y-axis. And if you integrate from minus a to a, that should give you 0. So without doing anything, I'll just say that this is 0. Now, of course, you can carry on the actual calculation. You can integrate by part and then do all the tedious things. I guarantee you that you will land up with the same result. Okay? Now, if you change this number to minus 2 to 5, of course, that's a different thing, right? You need to integrate. But if it's from minus 1 to 1, then you're guaranteed to have a 0. So that's an example of the odd function. Now, you will see this kind of problem very often. Now, why? You ask why. Well, let me give you a Gaussian distribution, a normal distribution. Typically, what you care will be the confidence interval of something, and you check the tails, or you check the stuff inside, then you're going to integrate things inside, right? So I can always shift the normal distribution from whatever center point back to 0. I integrate something from one tail to the other tail, I can give you 0, right? So those kind of calculation would be very, very handy if you know what you're doing, right? This is a even function, so you can do this calculation by doubling. But you can also have functions like this. This will come when you try to calculate the average. When you calculate the average, you want to multiply the number with the probability distribution. That can give you plus and minus. And then in that case, you will also get this odd function that will show up, right? So here you will get an even function. Here you will get an odd function. And these two formulas will help you solve the problem a lot quicker. So that's the thing about odd and even function. And let me, maybe I should just pause this because I don't think we're capturing anything here. OK, so let me move on and talk about the fundamental theorem calculus. It's another very useful tool that can help you deal with integration and also differentiation together. The theorem states as follows. You have a continuous function on an interval a and b, and then you want to integrate from a to x of this function. The dummy variable is t. Then you want to take the derivative with respect to x. Now, this x has to match with this x. See that? So you have two x here. This x has to match with this x. That will give you fx. So you integrate this function from a scalar to a variable x, and then you take the derivative of this guy. It's going to give you the fx. That's called the fundamental theorem calculus. Now, again, you ask, why do we need to learn this? When are you going to use it? Very soon, in Chapter 4, we're going to talk about cumulative distribution function. And that is a well-defined object. And the relationship between a probability density function and the cumulative distribution function is through this relationship. You will take a derivative with respect to your x for the cumulative distribution function, then you're going to get the density function. right? So you need to do this kind of exercise very often as we go to that chapter. So I just brought it up in case you haven't seen it, or if you've seen it before, just a good review of this material. So here's a corollary. If you have a function like this, ft, and then now the upper limit is no longer an x, but then it is gx, then you just do this f of gx, and then you have the derivative that comes out. Let me see if I have an example here. Okay, this is a pretty obvious example. This is called a Gaussian distribution. Now, of course, right now we haven't been able to recognize it, but later on you recognize this is a Gaussian distribution. This is a Gaussian distribution, or a normal distribution. It should look like this. Okay, it's a bell-shaped function. This function is a function in t. And then I'm going to integrate this function. Okay, I'm going to integrate this function from 0 to x minus mu. Okay, from 0 to x minus mu. So what I'm doing is that I'm going to start with this point. Okay, I'm going to start with this point. This is my 0. And I'm going to integrate up to a value. Let me call it x minus mu. This is my integral. Okay, so this is the upper limit. I'm going to integrate this function from 0 to this number. And then I'm going to take the derivative with respect to that. Okay, so you can imagine that this is a very complicated function. I'm going to do a lot. I need to first take the integration, and then I'm going to take the derivative. So imagine how you're going to do it. Well, let me just integrate this function first. Okay, but by the time you try to integrate, you realize this is actually not easy. How are you going to integrate this function? By parts? You have a square. You don't have an x outside. You don't have a t outside. How do you do by parts? Substitution? I don't even know how to do substitution. Okay, this is just a very difficult integral. In fact, there's no closed form solution for this integral. There's no closed form solution for this integral. But the good thing is that you actually have this derivative outside. I'm asking about this combination of derivative and the integration. So that can save your life a lot. And in fact, this one will give you directly this the result as follows. This is your ft. Okay, now you need to recognize this is d of dx, integration from 0 to something, and then you have this f of t, and then dt. No matter what happens, this result has to be f of that little thing here, and then you have this d dx of that little thing. This is the fundamental theorem calculus. Okay, so what I mean is that you have this f of t, and then you substitute this inside, so that has to be your x minus mu. So you have f of x minus mu. D of dx of x minus mu, d of dx of x minus mu, this is just d of dx. This is just 1. Sorry, this is just 1. Okay, so what do you end up having? Well, you just have this f evaluated at x minus mu, and this is going to be 1 over root 2 pi sigma squared e to the power minus x minus mu squared divided by 2 sigma squared. Okay, I can actually show you that this big integral and derivative will give you a very simple formula at the end. Questions? Now, okay, that's a good question. What are we trying to do? This is the area, right? Now, if you only integrate the area, you get this. However, if I integrate the area, let's see what will happen. Okay, so if I integrate starting from 0, if I integrate more, I will go up. Okay, and then ultimately, when I go to this plus infinity, I will go to a plateau. Correct? Right? Okay, so this function, it will be the integration from 0 to x minus mu of this creature here, and then dt. This is the function. I'm asking, what is the slope of this function? what is the slope of this function? Now, if you can continue on the negative side, you'll get this. Okay? I'm asking what is the slope of this function? And the only thing you have is, okay, I know how that will be the normal distribution, and I'm integrating the area. But I'm telling you, okay, integrate the area, find this curve, find the slope of this curve. Right? And this is why we're taking the derivative. And there's a beautiful thing here is that this is called the probability distribution function. This is called the density function. This is called a cumulative distribution function. And there's a derivative relationship between the two. Now, if I don't teach you this technique, when we go to chapter 4, and I show you this problem, and there's no way that you can go from here to there and go from here to there. Right? So this relationship is very, very useful as you're going from one to the other. Now then you can ask more questions. Why do we need to learn about this cumulative distribution function? As a matter of fact, this kind of distribution, it can be not very well defined. It may become a delta function, and you know the delta function is not really a function, right? However, a delta function, when you try to integrate, you get a step function. The step function is always well defined. Okay, and so as far as this mathematical properties are concerned, the cumulative distribution function is always a well-defined object, and so we want to use that, and then from there we can derive all the density functions. Okay, and so I'm bringing all these techniques up so that now you can practice a little bit about this fundamental theorem calculus, and as we go on and talk about chapter 4, it wouldn't be suddenly there's a monster that comes out, right, or from nowhere. This is where we are heading to. Okay, all right. So it is a very quick illustration of this tool. When you have integral, when you're derivative, you can combine them together to give you this final result. It's very easy. Just go inside, take out the function inside, and plug the value in, and then that will be the result. Okay, so that's called the fundamental theorem calculus. Is everyone good? Okay. I believe this should have been taught in calculus, if I remember correctly. Am I right? Okay. Okay, so let's move on. Just a couple words about algebra. We don't need that until the very end of our course. But then linear algebra will be the core as you move on to take advanced courses, for example, machine learning. Because here what we're learning in 302, they are all scalar random variables. Scalar random variable means that you only have one random variable. But very quickly, when you go up, you're going to deal with multiple random variables together. Just to give you an example, you have an image. Okay? An image that contains thousands of pixels or millions of pixels. Each one is a random variable. You're already dealing with an array of random variables. So in that case, these kind of linear algebra will be very helpful. Okay? So what I want to do here, just mention a couple notations, and then I'll skip the rest. Okay? I remember in your homework assignment, there's actually a programming problem. It's a very easy programming problem. Go to Python, MATLAB, type up a matrix, and then do some simple operation, and then plot out a couple figures. So that's the requirement for the homework. Matrix and vectors, they're all in bold symbols. They're all in bold symbols. You have columns, and then you have rows. I believe you should have learned a linear algebra course. If not, you should be able to learn it in very soon. I think that's required in your curriculum, a linear algebra course. Okay. Then what is most useful thing that at this stage that you need to know? Okay, at this stage, there's only the one thing that you need to know. It's called the inner product. Okay, that's only inner product. That's the only thing you need to know. Let's say I have an array of numbers. I call it x1 through xn. I call it a vector x. Now that's x. I put an underscore because I'm writing using my pen. And then you have this y vector. Okay, and I want to put a inner product. Inner product is denoted by this notation: x transpose y. X transpose y. So what I have here is that I'm going to write down this x and this y in the following form. Each vector has to be denoted as a column. Okay, always remember, all the vectors that are denoted as a column. So you have all the y1, y2 through yn. And then you have the other column, and this is called the x1 through xn. There is an operator called the transpose. Transpose is going to rotate your vector from a column to a row. So you have x1, x2 through xn. So you put them into this format. Then the inner product is going to be defined as x1 times y1 plus x2 times y2 plus all the way to xn times yn. So you have x1, y1 plus x2, y2 plus all the way to xn, yn. This is called the inner product. Okay? You ask, how can this be useful again, right? If I give you a matrix, I give you a vector, I ask multiply a matrix with a vector, then in fact every row it will be an inner product. So you just need to repeat this over and over. This inner product, the reason I mention it is that it actually has a lot of meaning. When you take the inner product, you're measuring some sort of angle between the two vectors. Okay? You're measuring the angle between two vectors. If your angle is less than 90 degrees, then the inner product has to be positive. If your angle is bigger than 90 degrees, then your inner product will be negative. This is extremely useful. Let's say I have data sets like this. Okay? Class 1 and class 2. Class 1 and class 2, they're on two sides of my decision boundary. And let's say I have a decision boundary. This is my candidate decision boundary. This is my vector, one vector, okay? A decision boundary can be represented by a vector. That's called a normal vector. I can do this thing called the inner product of all the points. Okay, I can just do this pairwise inner product for every single point. Check their inner product value. If my decision boundary is correct, everything on the right-hand side has to be positive. Everything on the left-hand side has to be negative. Why? Because this is my inner product, right? This is my normal vector of my decision boundary. And then if my inner product with this guy here, my angle will always be less than 90 degrees for anything on the left-hand side. It will always be less than 90 degrees for everything that's on the right-hand side. Okay? So if you're still puzzling, if this is my normal vector, this is my point, okay? I take the inner product here, this is my angle. It's less than 90 degrees. I look at this thing here, it will be less than 90 degrees. Okay? Now, what would happen if I have a really terrible classifier? So you have crosses, you have circles, and then let's say your classifier is this. Now, this is a terrible classifier. No one wants to build that classifier. But you can tell why this is a terrible classifier, because this is my normal vector, right? This is my normal vector. And then I can measure the angle. Well, positive, 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 right? Oh, negative, right? Angle bigger than 90 degrees, negative. Already I will know that this decision boundary is not good because I give you a negative inner product, right? Then you move around your decision boundary until you hit a point. Okay, everyone's positive on one side, everyone's negative on the other side, right? So why do we want to talk about inner product in statistics? Because whenever you try to build classifiers like these, you need that tool. Okay, so inner product is just not only a linear algebra thing that makes you work on problems, but it actually has a lot of usage. That's why I mentioned it here. Is that all right? Okay, we'll come back to this point later again, okay? All right, so I will skip that, and then let's move on to the fun part, okay, which is the combinatorics. Everything I've said here, you can find them in the textbook. The textbook has a lot of explanations, a lot of examples you can go through. If you want to watch the videos, past videos, they also recorded is also in great details. Okay. Now, for this in-person class, what I want to do is to talk about this combinatorics. chapter 1.5. Now, if you ever wonder, well, this professor is going really, really quick, okay, for this chapter. There's a reason, because chapter 1 is really for the sake of review, okay? As we go to chapter 2 and 3, it will be a lot slower. Chapter 1, since I guess quite a few of you here have already learned the material, I don't want to bore everyone, okay? But on the other hand, I want to make sure that everyone will have the same foundation as we move on to talk about the other chapters. All right, combinatorics. What is this all about? It's about counting events. Let's do the following experiment. Okay, let's do the following experiment. In this classroom, of course, we have more than 80 students. Let's make it a little bit easier. How about imagine that in this classroom we have 50 students? Okay, 50 students. Go ask around the birthday. How many of you, what is the probability that at least one pair of you will have the same birthday? Now, this is a very famous problem. It's called a birthday paradox, okay? Okay, so listen to the problem again. There are 50 students in a classroom, okay? You walk around, find out everyone's birthday. There will be an event. The event is called the two students will share the same birthday. This is one of the events, okay? So we, what is the probability that at least one pair of students will share the same birthday? Okay. Any thoughts? Now you need to start counting. 50 students, 365 days. I need to fill up these 365 days. That means I need at least 366 students to guarantee that at least 2 of them will have the same birthday. Right? This should be part of your thinking process. Am I right? Okay. All right. So let's do this. How many of you would think that this probability is very low? Okay. It's unlikely that at least a pair of students will have the same birthday. How many of you would think that this is a low probability? Okay, good. Okay, low. Okay, how we define low, it doesn't matter, right? Because you just think it's low. How many of you would think that this is going to be very high probability? Okay, very high probability. Can anyone give me a reason? Why do you think that this is going to be low? Anyone who voted for low? Yes. Each student having a unique birthday is very low. Okay. What about people will say that the probability that that at least one pair of students will be very high. At least one pair of students will have the same birthday will be really high. Right? We just asked about the reason why a pair of students having the same birthday would be really low. Okay, so that's one response here. Yes. Okay, so what is the can you summarize in a sentence or two? No. Okay. Anyone else? Yes. Okay. Uh-huh. Uh-huh. Mm-hmm. Okay, so we're getting there, right? So 40, 49, 50, around that number, and then there will be some multiplications, right? Hopefully that can show up somewhere. Okay, the gentleman at the top, any thought? Okay, so we're getting there. Okay, we're roughly getting there. The answer to this question is that the probability is close to 100%. Okay, it's almost guaranteed that you will get a pair of students, they will have the same birthday. This is kind of counterintuitive because, as I said, 365 days, if you need to fill up the 365 days, you need 366 students, right, to guarantee you to have the same birthday. Okay, so how does that work? That will require some tools, but before we talk about the tools, let me tell you the answer to this question, and then we can come back to the tools. There are 50 students in the classroom. What is the probability that at least one pair of students will have the same birthday? Okay, so the way of thinking is that imagine that you are the first guy. Okay, so the 50 students, they are lying outside. Okay, they're outside the classroom. As they are walking in, the first guy, there will be 365 seats. Imagine that in this classroom. So as the person walks in, he or she can choose the seat according to his or her birthday. Okay, so how many seats that he or she can choose? That would be first person. 365 seats that the person can choose, right? So the first person, you have 365 choices. Okay? Now, the second person comes in. We ask, well, if you don't want to have the same birthday, how many options would a person have? One less, it will be 364. The third person, you will have 363. Okay? And then you do this 50 times. That can roll all the 50 students, right? So the last one would be 316. Okay? And you count them, that will give you 50 students. Okay, so that's the number of choices as you go to the 50th student. The 50th student will have so many choices left. Okay. If you're not choosing this, then you are going to all overlap with someone else. Okay, I want to make sure that everyone has a unique birthday. What is the chance that everyone has a unique birthday? Let's calculate that first. And then 1 minus of that probability will be the probability that at least one pair will have the same birthday. You see the logic, right? So let's calculate the probability that everyone is different, and then calculate the 1 minus. So let's say you have 50 students in this case, okay? Then what will be the denominator? Well, the denominator is obvious, just 365. This is the probability for each one, right? 365. And you're going to multiply them. The denominator will tell you overall how many choices, the total number of choices that you have. The numerator will tell you how many effective number of choices that you can get. Okay? So you just take this ratio. That will give you a number. That's going to be a very, very small number. Okay? And then you do this 1 minus. That will be the probability. And if you plot this out, you can see that it is going to be something like this. Okay, so this is the probability. This is the number of students. And this transition is actually pretty sharp as you go through maybe 50. 50 is already here. Okay, as you go to 30 or 40, you are already in a very, very rapid rising slope. And if you go to 100, you guarantee almost 100% that 2 students will have the same birthday. So what is the technique over here? Of course, I'm showing you the counting process, right? But underneath, there are 2 things that we can use. One is called a permutation. The other one is called the combination. Now, notation-wise, it's good to know the notation. It's also good to know the formula. But I think it is even more important to know the counting principle, the principle of counting. Now, this is a good example here because I have already demonstrated the key element of this counting example. Why? Well, let's talk about this permutation first, and you will see why do I say that this example has already illustrated the principle. So this is 1.5. So if you flip to page number 3, you can see this is the definition of permutation. Okay. So let's say you have n balls, okay, and they're all having different colors. You want to pick k balls, okay, different color, k of those. You have n, and then you want to choose k without replacement, meaning that you put the you take a ball out and then you never put it back. Okay, if you put it back, it's called with replacement. That's a different thing. You take it out, you don't put it back, and then you ask how many configurations do you have. And by configurations, I mean that the ordering of the color balls, they matter. So red, green, and blue versus green, blue, and red, they are two different things. Okay. So as we go to talk about combination, then 2 red and 1 green, no matter how you order, you call that one configuration. Right? Here we red, red, and green, green, red, and red, they sort of different things. Okay? So the ordering matters. Okay? Order matters in this permutation. Then I ask, how many ways, how many configurations can you get from this n choose k event? The formula is given here. Okay, it's just pretty boring formula, and even if you memorize this, it's not going to help you solve any problem. But then the principle is the same as what we have demonstrated in the birthday problem. So you have n balls. Okay, you want to choose k. How do you do that? Well, you start with the n balls. You have, let's say you have 5. Okay, so the first guy has 5 options. Okay, 5 options to choose from. Red or green or blue or yellow or black. You have 5 options to choose from. As the person has picked the first ball, let's say the person has picked the red ball, then you only have 4 balls left. Right? So the options will be going down to 4. And then now you say you pick 3 balls. Okay, you have 5 balls and then you pick 3. Then you will just go 3 times. Okay. So that would be the k times, and then this is the total number of n balls. All right, and so you ask, what is the number of configurations? 5 times 4 times 3. 5 times 4 times 3. Okay, so that is the total number of configurations. And how do you write that down more precisely? You just write down 5 factorial divided by 3 factorial. 2 factorial, sorry. 5 factorial divided by 2 factorial. Now what is it? It would be 5 times 4 times 3 times 2 times 1 divided by 2 times 1. So cancel the 2 times 1, you get 5 times 4 times 3. That's called a permutation. Okay? If anyone has ever taught you what the permutation is, n factorial divided by n minus k factorial, forget about that. Just go to here, draw the balls, draw how many layers of balls, and then multiply them together, you get this permutation. It's that same concept. Okay? Nothing more complicated than that. Now, of course, we can make up very, very complicated problems on that, but let's just get the first principle. Okay. All right. So then what else can we do? Well, this is an illustration. So if you ever want to read it, 5 choices, you pick one, and then to go to the second round, you have 4 choices, and then you only have 3 choices. Right? So every route that you go, you're going to have one less combination that you can look for. Okay. So this is the permutation. So let me also talk about the combination. The combination says the following. You have n balls. They're all in different colors, and then you want to choose k of those. Now, the order does not matter. The order does not matter. So what that means is that now I have this 1 and 2 and 3. This is the same as 1 and 3 and 2. Okay. The only thing that will become different would be 1 and 4 and 5. Now, that's different. Okay? But this combo and this combo, they will be quantified as the same thing. So how do we solve this problem? Well, first of all, you still do this 5 balls, choose 3, right? 5 times 4 times 3. So you have this total number of configurations. But then you go inside, okay? You say, okay, so now I have these 3 balls. So this is my first ball, second ball, and 3 balls, the third ball. So I look at those, and then I say, the combinations, okay? By shuffling the order of this 1 and 2 and 3, doesn't matter, right? So I just need to divide this permutation, which is n factorial divided by n minus k factorial, divide by something. And what is that something? That something has to be how many balls do you have, and therefore how many combinations can you get. So if I have 3 balls, then I mean that I will have 1, 2, 3, 3, 2, 1, 1, 3, 2. So I ask how many different orderings can I get? That's very simple. That's just 3 times 2 times 1. Okay, that would be the total number of orderings that you can get. So that would be what? Well, if you have k of those, that would just be k factorial. So we divide by k factorial. That is called the total number of configurations without worrying about the order. And that's called a combination. You see? Okay? So the 2 principles is very simple. Counting by listing all the number of layers. Okay? And then if you care about the ordering, you're done. Permutation. If you do not care about the ordering, you just divide by the total number of ordering combos. Okay, that will give you a k factorial. So that will give you the combination. Okay? So a lot of problems that we're going to counter will be as simple as this. Okay, so just grab these 2 principles that can help you solve quite a bit of problems. All right. So I hope this very fast overview of the combination, permutation, and also the birthday paradox gives you a little bit idea of the tools that we're going to use. So starting on Monday, as we come back, we'll go into probability. So that will be chapter 2. Okay, so I'll see you on Monday.